So yeah, today we're going to move on to a topic called regular expressions. But before I do that, I want to try to clarify something that I don't think the book was terribly clear about until later. But so let me just remind you that in a DFA, the delta transition, the transition function, is Q cross sigma. This means all the states and all of the characters in the alphabet. And what that implies implicitly is that in a DFA, let's say our alphabet is just binary, A and B, and here we're at some state. In the DFA, there has to be some edge out with an A and some edge out with a B. It could be back to itself or something. So when we started talking about NFAs, all of a sudden we started seeing states that didn't have necessarily an edge for each character in the alphabet. And then the interpretation is that if the computation gets to that state and sees a character that does not correspond to any of the edges going out, then that computation dies. Not the whole NFA, but just that particular computation in the NFA dies. But that's not a possibility for DFAs. In DFAs, it's required that you have you have an edge out with every character in the alphabet. Okay, so there is a question in the problems in the book. I don't know whether this is one that was assigned or not, but I know somebody talked about it in office hours, which was to just make a DFA, or sorry, an NFA for that simple language. It just has the zero in it. Was that one of the ones that was assigned? I don't remember. At any rate, so if you want to have an NFA like that, I mean, that's just such a trivial language, okay? It looks like this, then you have an A, then you have an except state, and, sorry, a zero, not an A zero, and then you have an except state. So if the string that comes in is just a single zero, then that's fine, it's accepted. If the string is, let's say the alphabet here is just zeros anyway. But if the string is multiple zeros, more than one zero, then what happens? You read the first one, it gets there, and then when you see the second zero in the string, well, there's no edge out of here with a zero, so you're not at the end of the string, so that computation dies, and this was the only way to branch anyway. So this is an NFA that recognizes this language, and that's a perfectly good NFA that does that. But this would not qualify as a DFA because in this state, okay, there's no transition rule for what should be done when in that particular state you see a zero. In a DFA, it requires that you specify what should be done. Okay, so in fact, how would you write a DFA for this language? For this language, we know there is one because here's an NFA, and anything that's accepted, any language that's recognized by an NFA must be recognized by some DFA. Yeah.
You just have another state right after, and then you keep looping back into the next.
Yeah. So this would be the DFA. Zero, and then this is still an accept state, but if you see another zero, you go over to some other state which is not an accept state, and then you have a zero there, and that's a DFA, okay, that accepts the same language. If it's just a single zero, you're in the accept state and you're done. You're at the end of your string. If it's multiple zeros, then you go on to a state that's not an accept state, and you stay there until the string is finished, until you finish processing the string, and then the computation ends, but you're not in an accept state, and so that's a reject. Okay? So this is a distinction I just wanted to emphasize, because I know that in the office hour, when somebody was asking about this particular problem, I think we said, well, this is just this is a DFA and an NFA, but in fact that's not true. This is only an NFA, and this is the DFA. Yeah.
Why can't you do a self call to 0 in the accept state?
Oh, if I did this one?
Or for the DFA?
Sorry, in the DFA? Well, if you did that, and then you wouldn't have this one, right? Then this would accept, for example, 2 zeros. Okay, if you had a string of 2 zeros, you would go 0, 0, ending up in the accept state, so that would accept 2 zeros. But 2 zeros are not in that language. Okay, this is the language that contains one string. It's the string that only has a single 0. It's a very trivial language. So that's why in the DFA we needed this thing, 0, and then like that. Okay, now how in the formal specifications of NFAs, how do they allow this when in the formal specifications of a DFA they don't allow any state to have well, they require, let's put it that way, they require that in any state there's an edge out with each character in the alphabet. How is it in the formal specifications of an NFA that that's permitted in NFAs? Well, in NFA, the transition function is described as states cross, first of all, it's the alphabet augmented with the epsilon sign, but that's not what is the key thing. This is, it is a map or a function from Q cross sigma epsilon to the power set of Q. This means all possible subsets of Q. So this is a subset of states. Now that subset of states includes a very particular subset, which is the empty set. Okay? Including the empty set. So really, if you were to write out the table, and they do this in the book, if you were to write out the table of the transition functions for this NFA, then when you're in this state, and the way it's written out, let's call this Q1 and Q2. So Q1, Q2. When you're in Q1 and you see a 0, you go to Q2. Okay? But when you're in Q2, the way you write it out in the table, when you're in Q2 and you see a 0, what subset of states do you go to? The empty state. Okay, the empty subset. Okay? All right? So that's the way you formally write what this NFA is doing, is it's going nowhere when it sees a 0, because this is the empty subset of states, which means, well, it's going nowhere. That's just the formal mathematical way of saying it's going nowhere. All right? So I'm just pointing out that the formalism for an NFA allowed this kind of machine. But the formalism for a DFA did not allow that kind of machine. Okay, yeah.
So the bottom diagram right here,
yeah.
How could that be a DFA without transitions, in case there's a 1 inside?
Well, there's the alphabet is just a single 0.
Oh,
okay, so all you have to do is say what to do for each character in the alphabet. Okay. If you get a string that's completely outside the alphabet, then that sort of violates the whole game plan. Yeah.
What did you mean earlier when you said you can have 2 zeros? Isn't 0 in the output when you have 2 consecutive zeros, and you just it would just always be in the except if you had at the except state you have a loop back with itself 0. zero.
I'm not quite sure I understand your question, but here we're talking about the language which only has one string, and that string is just a single zero.
Also, that just means that the language can only be one character long.
Yeah, right. The language contains one string, and that one string is one character long, namely it's the zero. Okay, so if you had a self loop here, you would be accepting strings that had more than one zero, and that would be outside the language.
What's the point of having it continue on past the accept statement?
What's the point of having this? Well, the point is that this is now a legitimate DFA. According to this definition, it has an out arrow for every character in the alphabet. And in fact, it recognizes this language. So the point of it is that it is a legitimate DFA. Okay. Now, you can, if somehow by shorthand you got used to saying this was a DFA, okay, you could always then add on things like this to make it a legitimate DFA. Out of the accept state, you just, if there wasn't supposed to be, if there's no way to go with an extra character zero, then you can always just add on a little gadget like that and make it a legitimate DFA. Okay. But anyway, this example just shows you that, at least in this particular little case, and it does come up frequently, that it's more compact to write an NFA than a DFA. Okay, it's just, and so a lot of times when the homework is asking, or the book is asking you to find an NFA with a specified number of states, they're trying to get you to see that you can use fewer states in those examples with an NFA than with a DFA. Okay. All right. Anyway, this is very, very, I wouldn't call it nitpicking, but it's very precise, pedantic point. And I hope everybody gets it, but it's certainly not the core of what we're trying to teach you. But it's a distinction that I don't think the book makes until later on. But when it's talking about DFA, it doesn't really emphasize the fact that you have to have an out arrow from every state, including the accept states, for every character in the alphabet. Okay, let's go on to the main topic of today. So, the main topic of today is regular expressions. And this regular expressions are sometimes abbreviated as a Regex. And this regular expressions actually, I mentioned at the beginning, the first lecture of the course, and I talked about it in office hours to somebody, that in the whole computer science curriculum, in terms of which courses are really practical and which courses are more theoretical, this is on the more theoretical end and probably the least practical course that we have in the curriculum. But regular expressions are actually very widely used, and it's useful to learn about them and to learn something about their power, and ultimately we'll learn about their limitations as well. And so regular expressions really come up a lot in compiler classes and programming languages and searching and so on. So a regular expression really is a shorthand for describing regular languages. So far, we have two ways of describing a regular language. If you have a regular language in mind, well, actually, maybe I should say there are three ways of describing a regular language, and only two of them that not only describe the language but prove that it's regular. What are the two ways? If I want to convey to you, describe to you a particular language that I claim is a regular language, how do I do that?
Build a DFA.
Yeah, I can show you a DFA for it, or I can show you an NFA for it. Okay, because we know that DFAs and the class of DFAs and the class of NFAs recognize exactly the same set of languages, namely the regular languages. Okay, so those are the two ways we have so far of really describing a language and at the same time carrying with it a proof that it really is a regular language. There's a third way of describing a regular language that doesn't necessarily carry the proof. What's that? Yeah. Well, we haven't learned regular expressions yet. Okay. This is the segue into regular expressions. What's the third way? Yeah.
Simply listing all the strings in the language.
Okay, listing all the strings, if it's finite language, of course the language might be infinite, so that doesn't necessarily, but you're right, if we can do it, that's certainly, okay, so that's 4 ways. What's the third way I was thinking of? It's just sort of, the English description or the set theoretic description that we've done many times. We've said, language A, well, you're right here even. This is a description in terms of, this is in fact listing all the strings, but I could have A is equal to the set of strings such that W has an even number of characters. Okay, so that describes a language. It describes a set of strings. It might be a regular language. Is this regular or not? Yeah, but it looks regular. I mean, anyway, you should find it easy to find a DFA for that. But my point is that here describes a language, but it doesn't necessarily, in that description, carry along with it a demonstration that it's regular, because it doesn't show you the DFA or the NFA for it, and the same thing here. Okay, anyway, we have these 3 or 4 different ways of describing a language. A regular expression is another way which will not only describe the language, but carry along with it a proof or a demonstration that it's regular once we understand that regular expressions, the class of languages that are described by regular expressions are exactly the regular languages. And that takes a proof, which we'll do today. So I want to describe what a regular expression is and then give the proof that the class of languages that are described by regular expressions are exactly the regular languages, or is exactly. A class is a singular. Anyway, the grammar of what I just said was all messed up, but I think you understood it. Okay, so here's an example of a regular expression on 0 star. And what this is the language that consists initially of a 0 or a 1, followed by some number of zeros, including the possibility of 0 zeros. Okay, so 0 star is this operation. The star operation is any number of repetitions of what that particular string is, or regular expression is there. This happens to be just a 0. And this is the union of a 0 or a 1. Okay, so you could probably, it's easy to construct an NFA for this. No, I don't want to do that. A 0 or a 1. Okay, here's my start state. And we could epsilon onto there. But we don't even need to do that. This is any number of zeros, any number of zeros, okay? So that looks like a perfectly good NFA for that. Does that seem right? I just did this on the spot. Very dangerous to do anything I haven't prepared. But you either take a 0, followed by any number of zeros, or you take a 1 followed by any number of zeros, and so this is an NFA for that regular expression. So I haven't told you the rules of what a regular expression is, but I'm just starting out with this particular example, and hopefully this doesn't seem too weird of a way of describing the language that's recognized by this NFA. Okay, so let me be a little more formal. After that, just one little example. A definition, a regular expression we'll call it R, is what? Well, it is either, one possibility for it, it's just a single character for some A in the alphabet. Because we have an alphabet which is implied. You can make it explicit if you want. In this case, it's 0, 1. So there is some alphabet that's being used for the regular expressions, not necessarily 0, 1. It could be any particular alphabet you have in mind, but you do ultimately have to say what it is if you want to be totally formal. Usually what happens is just the alphabet is just a set of the individual characters that are found in the regular expression. Okay. So a regular expression R is just A for some character in a specified alphabet, or it's the epsilon, the empty string that we know about, or it's the empty set, okay? And or it's R1 union R2 with parentheses around them, okay? Where R1 and R2 are regular expressions. All right? Unfortunately, I've run out of board space. Let me just go up here. Circular rotation. Or 5, it's R1 concatenate R2, where again, R1 and R2 are regular expressions. Okay. Or 6, it's R1 star with parentheses around it. So this is a regular expression starred. So that means any number of repetitions of that regular expression, okay? And then parentheses around that. Okay, so in fact, let's look at the regular expression that I had a minute ago. Right, do it in here. It was 0 union 1 followed by 0 star. So yeah, these are operators, okay, union and concatenation and star. So this looks bad. This is colloquial, but actually isn't following completely the definition, okay? Because let's try to parse this with this definition, okay? Is this a regular expression, just the 0 by itself?
Yes.
It's a regular expression by this rule, okay? That's a regular expression. Is 1 a regular expression? Yeah, okay. Is 0 union 1 with parentheses around it a regular expression? Yes, that comes from here. So this is a regular expression. Okay. Is 0 a regular expression? Yes. Okay. Is 0 star a regular expression according to these rules? Well, not quite, because here it says there should be parentheses. Okay, that's why I say this is sort of colloquial. We've taken some shortcuts. All right, so if I really wanted to be completely loyal to this definition, I should have written it that way. And then this is a regular expression. Okay? And then, so this is a regular expression and this is a regular expression. So according to these rules, is this a regular expression? Yeah, it's not quite. I mean, it is in terms of we know that this implicitly means that there's a concatenation, but if we actually take the literal rule here, we should have a regular expression, here's one, concatenated, and so we should have the concatenation in there, followed by that regular expression, okay? And then this says to put parentheses around them. All right. So if you followed this definition exactly, then this would be the complete formal specification of that regular expression. But just as if we were going to write A times B in normal arithmetic, okay, then this can certainly is usually written just AB, right? And context, if I'm talking about, this is not a string now, this is just regular multiplication and arithmetic, people write AB as opposed to A times B, or they can write that. So similarly, the concatenation is usually just implied by the fact that these two regular expressions are next to each other. And then this set of parentheses seems kind of extraneous, and similarly this seems kind of extraneous. You can get away with this, but if you follow the absolute definitions, the formal definitions here, we would need those extra parentheses and then the extra concatenation operator. Okay, so this definition is a recursive definition, right? Because it's defining what a regular expression is, R, in terms of other regular expressions. So why isn't that circular? Yeah.
It has base cases.
Because what?
It has base cases.
It has base cases, and the references to other regular expressions are to smaller regular expressions. Okay, so R is, if it's a regular expression of this type, it's made up of two regular expressions which are necessarily parts of that, and so therefore are smaller. So if you take a regular expression, and just as we did, and use this definition to parse it, to demonstrate that in fact it is a regular expression, you don't go in circles. You go from one regular expression to smaller regular expressions and so on. If you're going to go top down, we went bottom up actually. Went from smaller regular expressions to bigger ones. But the definition itself is a recursive definition. And it has base cases. That's what was pointed out here. That recursive defining, if you go from the full regular expression down to smaller and smaller regular expressions, that process stops because you either end up with a symbol, a character from the alphabet, or you could end up with the empty string, or you could end up with the empty language. By the way, these two things are not the same. Okay, this is a string. It's an empty string. You can't see it. Okay, but it exists. The empty language has nothing in it. It doesn't even have the empty string in it. Okay, so that's a distinction that's important to make. It's like the number 0 is a 0. Okay, if I have 0 objects on the table, that is a number, a particular number of objects. Okay, if I have no number of objects on the table, then we have no. I'm not sure this analogy is perfectly right, but we have no information about how many objects are on the table. If I make the statement, does everybody get that these are different? My analogy didn't quite work, but all right. So let's see some. Actually, maybe another example of a regular expression. Let's just make up one. So 0 or 1 star dot 0 0. Okay, that's okay. So this is sort of a. Well, all right. This is a regular expression because it's just a single character. This is a regular expression because it's a single character. This is a regular expression because it's the union of two regular expressions followed by parentheses. This is a regular expression because it's a star of a regular expression followed by parentheses. 0 is a regular expression. 0 is another regular expression. What about 0 0? Well, yeah, it's colloquially a regular expression. There's an implied concatenation there. Okay, so this is kind of a hybrid, not quite right, but it's the way we really do things in practice. So this is a regular expression because this is the concatenation of two regular expressions, and I actually even have parentheses around them, and then I have a regular expression here and a regular expression here, and this is the concatenation of a regular expression it doesn't completely satisfy the definition because, what's what? It's missing the parentheses, yeah. So since we're going to violate the law, I might as well go all the way and just get rid of that anyway. So this is more typically how this is written, or you might even get rid of those. It would be common to see that as a regular expression. But I'm saying that when you write out a regular expression or something that you claim is a regular expression, you should be able to go through this kind of parsing that I just did, breaking down the full regular expression into its smaller pieces according to this definition. And I'm sure I don't think I had a homework exercise like that, but I should have. And you should try one of those maybe for next time. Next homework I'll put one like that or a couple like that, where you have to demonstrate through such a parsing that it is a regular expression. And anyway, it sounds like a very good type of question for an exam. Anyway, so hopefully everybody's understanding that and what a parse means to do that. Okay, so let's see some things that you can figure out about regular expressions. Oh, by the way, here's another shorthand. It's not specifically in the definition here, but it's again what people often use. R plus is R star. Okay, so a regular expression plus is the same as, I shouldn't have equal, I should have three lines here, which means this is equivalent to, or this is defined as, some regular expression followed by the same regular expression starred. Okay? So what this means is that you have at least one regular expression there, one instance of that regular expression. So this doesn't allow the empty string. Okay? So this is actually what I just said is it doesn't allow the empty string. Is that true or not? Yeah, what if R is the empty string? R could be the empty string, okay, which is a permitted regular expression. So if you have the empty string to the plus, then that's saying, well, you need the empty string and then some number of empty strings, and it could be 0 or it could be multiple. You know, when you get into this kind of stuff, it's too weird and kind of degenerate. But so I think one would have to say that the empty string isn't here, because you could have that followed by 0 of these, and so that's certainly so this language would allow the empty string, but try not to focus on the really degenerate things. Anyway, that's what plus means. It means at least one instance of this regular expression. Okay, could be any number, but not 0 of them. Well, with that notation, how can we write our star? This is any number of them, including the possibility of 0 of them, and so this is R star union the empty string. Okay, and this is a regular expression. So let me point out again, this is a regular expression too, or a description of a regular expression abstractly. This is some regular expression concatenated with that regular expression starred. So this is describing a regular expression in an abstract way. This is also describing a regular expression in the abstract way. It's whatever this regular expression is to the star union that regular expression. Okay? And we know the union of two regular expressions is a regular expression. Okay. Another shorthand is R to the K, and that's K repetitions, or K concatenations of R. So K times. And so that's a shorthand for a regular expression as well. Because if R is a regular expression, this is a regular expression concatenated with this, And then inductively, this is a regular expression because this is a regular expression concatenated with that, and so on. Okay, so those are some sort of higher level rules about regular expressions, and also introducing particular shorthands. This is a shorthand, this is a shorthand. Okay. Now, zero star, oh, I see, 0 star, 1 0, no, 1 0 star. Okay. So I've written down, I have in my notes here some particular regular expressions. I think they're, on my notes here it says page 65, so these are probably listed on page 65. What we want to do is just look at these regular expressions, and say in words, what regular language is this describing? Yeah. It's a string that has just exactly 1, 1, right. So you could have any number of zeros, including none, followed by a single 1, followed by any number of zeros, including none. So this is just any binary string that has exactly 1, 1. What is this one? Sigma star 1 sigma star. Okay. Yeah. What's this one? Yeah.
Any string that contains at least 1, 1.
Yeah, this is any string that contains at least 1, 1. Okay, this was exactly 1, 1. This is at least 1, 1. And by the way, the sigma star, where does that come into the formal definition of a regular expression? Okay. Well, again, that's sort of a shorthand. The sigma, we have to think of that as the union of all the characters that happen to be in, these are the characters in sigma. So sigma is an alphabet, okay? But in terms of the actual formal definition of a regular expression, why is it permitted to put sigma star in the regular expression is because now this is a shorthand for the union of all the individual characters that are in the alphabet. Each individual character is a regular expression, right? And the union of regular expressions, union of two regular expressions is a regular expression, and therefore you can see that the union of any number of regular expressions is a regular expression. And so that's what this is a shorthand for. Yeah?
I'm just trying to clear this. Sigma is the set 0, 1 here, right?
The what?
Sigma is the set 0, 1 here, right?
Oh, okay, so yes, in this here, yes, it was implied that the sigma was going to be 0, 1.
Oh, it doesn't matter.
But we didn't really, here I was just showing you if, I was sort of doing a little kind of example where let's just assume sigma is the letters in the English alphabet, A through Z.
Before, but I'm realizing, for when you say at least 1, 1, it doesn't matter what sigma is.
Yeah, that's true actually, right. Yeah.
I was trying to understand.
Yeah. Yeah, it's sort of, this was implied that it was binary. In fact, I think I probably said it was binary. And here this example is a different sigma. Okay, it's just an example that when you see a sigma and you know what the alphabet is, then formally you can think of that sigma as a shorthand for the union of all the individual characters in sigma. Probably if I'd never said this, nobody would have asked me about it. I mean, this is this kind of a pedantic point for people who are really, really into the formalism. And you would notice that, hey, we don't have I'm saying this is a regular expression. Well, where is sigma in my definition of what's permissible under a regular expression? It's not there anywhere. So you would have been right to have called me on that. But would anybody have actually done it? Called me on that? Probably not. Okay. Okay, so that's another example. Now what's this one? Now that we've allowed sigma as a character, as a symbol that we can use in a regular expression. Yeah? Yeah, okay, so this is all the strings that are a multiple of 2. What's another way of saying a multiple of 2? An even number, yeah. These are all the strings over that alphabet, over the symbols in that alphabet that have even length. Okay? So strings of even length, including the empty string, which has even length because it has length 0. Okay, now here's one that's not totally intuitive, but this is the way this works. Okay, so this is the this is a regular expression. This is a single character in the alphabet. Starred, that's permitted. We have a regular expression starred, although we should be putting parentheses around it, but we're using the convention, we're dropping that. Concatenated with the empty set, or the symbol for the empty set. Well, the symbol for the empty set is a permissible regular expression. So this is a regular expression concatenated with this regular expression. But what language does it define? Yeah. This is the empty set. This is the same thing as the empty language. There's nothing in there. By the way, what's a DFA for the empty language? We're saying the empty language is regular, so it better be recognized by some DFA. Yeah. It's just the start state and no final state. Yeah. So the DFA for this is just that. Okay. So, or you call that, probably better to call that an NFA, okay? But this accepts nothing. It doesn't even accept the empty string, okay? It doesn't accept the empty string because there's no final state, okay? So this is the NFA for the empty language. And if you have 1 star or even sigma star, anything, followed by concatenated with the empty language, that's the same thing as the empty language. Okay, so that's a something you have to meditate on a little bit. And what about this one? The empty language to the star. What's that? What's another way of putting that one? Yeah. Okay, yeah, you know what? I don't think you can think this through. I mean, I would just take this as an axiom, as another rule of regular expressions, and it is so degenerate and weird, it doesn't really come up. But it's really this. Okay, and you can kind of convince yourself that that's sensible by saying, well, this is any number of times that we have the empty language, including none of them. Okay, so there's no empty language at all, and so that's the empty string. Again, I would put this A as a axiom as opposed to something that you ought to be able to figure out, and B, it's not going to happen. Okay, it's just too weird, but it is there on page 65, so I thought I would mention it. Okay. Some other facts that are, this one is important. R union. So what is, if you have a regular expression and you have this regular expression and you take the union of those, that's a regular expression. And what is a simpler regular expression that describes that one? Just R itself, yeah. So here we have the empty language operating in a sensible, in a more sensible way, whereas here we're saying a regular expression concatenated with the empty, with this symbol is that empty language. And R concatenated with the empty string, that's also equivalent to R. Okay, so whatever language is described by this regular expression, if you concatenate on that an epsilon, this regular expression is just describing that regular language. Yeah. R union epsilon, what is this? Well, let me just ask this. Is this equivalent to R?
Yeah.
Who said not necessarily? Yeah, why?
You don't need to have the empty string in regular language.
Yeah, right. This is not necessary. This might be, depending on what R is, this could be the same as R. But if R does not have the empty string in it, then this is actually, this describes a language which contains one more string than this one, namely the empty string. Okay, so they would be equivalent if R already contained, if R was a regular expression that already defined a language that contained epsilon, but otherwise they're not equivalent. So not necessarily. Sometimes yes and sometimes no. R concatenated with the empty language, is that necessarily R? Or can it be R? Let's put it that way. This is sort of a stupid question, frankly. If R is itself the empty language, then this is equal to the empty language, which is equal to R. So that's fine. But at any rate, this is always equal to the empty language. Okay. Everybody comfortable now with what regular expressions are and some of the rules about shorthands and a formal definition of what they are and the fact that we're going to use shorthands and throw away parentheses when we can get rid of them, throw away the concatenation symbol. I think that's always permissible. I need to tell you one more thing. So we have we have three operators in regular expressions, right? Three operators. Namely, we have union, we have concatenation, and we have star. Okay? And there's a precedence, an operator precedence. Just like if we were talking about arithmetic, we have plus, minus, multiply, and divide. Okay? Which operation between plus, minus, multiply, and divide has greatest precedence? Actually, there can be ties, right? Let's just say plus and multiply. Okay, so if you see, A plus B times C, and you don't have any parentheses in there, what's the order in which you do those operations? You do the multiplication first, right? That has higher precedence, and then you do the addition to you add A to what B times C is. If you did A plus B first and then multiplied by C, you would generally get a different answer. So precedence matters. And of course, you can break precedence. You can break the normal precedence by using parentheses. So if I wanted A plus B to be done first, I can put parentheses there, and then that puts the multiplication. Well, in regular expressions, the top precedence is, anyway, this is 1. No, I'm getting, yeah, I think that's fine to say that. Yeah. If you have, right, yeah, that's number 1. What's number 2? Well, this is number 2, and this is number 3. So, anyway, the precedence order there, and but unless we use parentheses to change the normal precedence order. Okay, so in fact, oftentimes we'll need parentheses in there to specify exactly the order that we want. Okay, now let's prove something. Page 1, page 2, page 3. Page 1. Yeah, okay. So the following thing. So we're going to prove the following theorem, and we're going to do it in two different directions. Theorem, a language is regular if and only if it is described by some regular expression. Okay? So that means if you have a regular expression, the language that it describes is in fact a regular language, which means there should be a DFA for that language. Also, there should be an NFA for that language. And conversely, if you have a language that's regular, so that means that there's a DFA or NFA for that language, then you should be able to come up with a regular expression for it. So the class of languages described by regular expressions is exactly the regular languages, which is something I said at the beginning, but we want to actually do that formally and show how to do that. And we're going to do both of those constructively. That is, we're going to go from taking a regular expression and show how to build an NFA from that regular expression. And then we're going to do the converse, where we take a DFA. Actually, it's the way the proof starts out with. You take a DFA and you build a regular expression that specifies, it describes exactly the same language. Okay, so two different directions. So the easy direction, or the easier of the two directions, is if some language A is described by a regular expression R, then A is regular. A is a regular language. Actually, there's another notation that's used here. L of R is the language described by R. Okay, so R is a regular expression. L of R, that's the language that's described by the regular expression R. So anyway, here we're saying that if A is described by some regular expression R, then A is regular. And or I could have said L of R is regular. It's a regular expression. It's a regular language. Okay? Okay, so how does the proof go for that? Well, we're going to parse. So we're given a regular expression R. And what we're going to do is we're going to parse R according to these rules. Just like we did in the example, in the various examples where we parsed a particular regular expression to show you that it was in fact a regular expression, break it down into smaller regular expressions, or actually we went up by taking the smallest regular expressions in there and then building upward to show that the larger regular expressions or larger pieces of that what we claimed was a regular expression really was a regular expression. And as we do this parse, I'm going to show you how to build the NFA that is associated with that part of the parse. And as we do the parsing, we're going to be putting those NFAs together in legal ways that create an NFA in the end for the same language that the regular expression describes. Okay, so we're given a regular expression R. And what's sort of the easiest case is that R is a single character, let's say A, in sigma. Okay? So I want an NFA that recognizes the language described by this regular expression. So what's an NFA that just recognizes the single character A? I just want an NFA that recognizes the language that only contains a single string in it. That single string happens to be the character A. Yeah?
So the start state and an accept state is like second state is the accept state, and they're connected by transitions.
Yeah, you could have that. Okay? So that is a NFA that just accepts the single character A, right? By the way, is that a DFA? No, it's not a DFA. Just as we were talking about at the beginning of the lecture, it's not a DFA because there's no out edge here. Okay, so that was sort of the trivial case. Now, number two, what if R is the empty string? Again, what we're trying to do here is to show that there's an NFA for each regular expression, and we're building up the NFA in the same way that we would be building up the regular expression by following the formal definition of what a regular expression is. So you would be building it up. You'd be building up the NFA from the inside out, from the smallest part of the regular expression outwards. And this is for the individual small elements. When you just have a single character, there's an NFA for that. This NFA recognizes the same language that's described by the regular expression consisting just of a single character. What about the NFA for the empty string? Well, we've looked at those before. What's that one? Yeah.
Is it a single state that's both the start and accept, and no transitions anywhere?
A single state with yeah, okay, that's fine. All right. We don't even have to put an epsilon on there. This would be fine. It just that's the start state and the accept state, and therefore the only thing it accepts is the empty string, which is there. Okay. All right, number three. Seem to be losing my voice. Three, what happens when R is the empty language?
No accept states.
Yeah, well, no what? No accept states, exactly right, yeah. So there's the NFA for that one. Okay, 4. All right, so now if we have a regular expression, which is the union of two regular expressions, how do we build an NFA that recognizes the same language as described by this regular expression? Well, back when we were talking about NFAs and what you can do with them, or what NFAs allow, how do we know that NFAs recognize the union of two regular languages? Yeah. Yeah, right. We just, here's the NFA for R1, and it has some start state, okay? And here's the NFA for R2, and it has some start state, okay? But we want the NFA for the union of these, and we've seen this before. You have a new start state, and then it goes with an epsilon transition over to that start state, and an epsilon transition over to that start state. And this now is an NFA for the language that's described by this regular expression. Okay, so we have an NFA that recognizes the same language that's being described by this regular expression. By the way, how do we know that we have an NFA for R1? Okay, yeah.
If we can establish recursively, like if we can establish that all regular expressions can have an NFA, then recursively R1 and R2 have to.
Yeah, I mean, in a sense, we're doing this construction from the smaller regular expressions up to the bigger ones. So at the point at which we would apply this, we've already processed R1, and we've processed R2, and namely, that means we've already figured out an NFA for R1 and R2 in this whole procedure. But you're sort of right in the sense that you're also right that until I finish everything, I can't really say for sure there is an NFA for this one. But once I've finished the entire set of rules, then the procedure is clear that if we go from small regular expressions up to bigger regular expressions, once I've processed these smaller ones in this, at the point where I'm going to do the union, then these are, there'll be NFAs for those as well. Okay. Because these regular expressions might have in them some, like concatenation, which we haven't looked at yet. All right. 5. What happens when this is a regular expression, this concatenation of two regular expressions, and this is our full regular expression. How do I build an NFA for this one? Well, this is exactly what we did earlier when we were talking about NFAs, that you can concatenate two NFAs. So the construction here is the construction we're going to use in building the NFA for the regular expression as we're parsing the regular expression, bottom up, is exactly the same construction that we used to concatenate two NFAs. So here you have the NFA for R1, here you have the NFA for R2. Here were the accept states for R1. Here was the start state. And here was the start state for R2. What do you do? How do you tie these two NFAs together? Yes? Yeah, you make these epsilons, and also, what else do you do? These, which had been accept states, now just become regular states. They're no longer accept states. Okay. All right. And then 6 is the star operation. And again, it's the same idea. I'll let you review how you make an NFA for the star of another of the language described by recognized by an NFA. Okay. So, okay, I know I've done this abstractly, but are you beginning to see the idea of how we're going to constructively go from a regular expression to an NFA such that that NFA recognizes exactly the same language that the regular expression is describing? I did this abstractly, but I hope everybody is beginning to get the idea, even if you might not be able to do it yourself. So let's actually do an example. So we need this board because that's the anyway. We need this board. I guess we need all but the first one. Okay, AB union A star. Okay, so this is a regular expression. It's in shorthand. We don't have all the intermediates, all the symbols. This is a concatenation of A and B. This is the star of this regular expression. Okay, According to the formal, we should have another set of parentheses, but again, this is a perfectly good regular expression. All right. Let's do the NFA for this. Well, we need the NFA for A. Okay. So that is A goes to the except state. Okay, so that's an NFA for this A. It's an NFA for that A. All right. We'd actually have two of them for each. Okay, I'll write that again. Input A except state. Okay, we want an NFA for B. There's an NFA for B. Okay, now we want an NFA for A concatenated with B. All right, what does that look like? How do you concatenate together two NFAs? We just did it over there abstractly, but here we're doing it in this particular example. Now let's not always see the same hands. Okay, somebody else, yeah. Yeah, okay. This is an epsilon transition. It's going from the accept state of the first one to the start state of the second one, and then we make that a normal state. Okay, so this is now this is the NFA for AB. Okay, it accepts A, B. All right. Then we want to take the union of this regular expression. We want to take the union of this regular expression with this regular expression, and we want an NFA that recognizes the same language that's described by this regular expression. Okay, so we have the NFA that recognizes the language described by that regular expression. We have the NFA that recognizes the language described by that regular expression, and we want an NFA that recognizes the same language that's described by the union of these two regular expressions. Help me out here. What do I do?
You start state that.
Right. Okay. A little bit messy the way I wrote these, the way I drew these, but here's a new start state. Okay, and it goes to that one by an epsilon, and it goes to that one by an epsilon. Right. So that's now an NFA for AB union A. Okay? And now this regular expression has a star. Okay? So now we this regular expression has a star. So now we want an NFA that recognizes the same language that's described by this regular expression. We have the regular expression for this part. Now we're doing a star. So what's the NFA for that whole regular expression? Well, we remember what the NFA rules were for implementing a star, and that's the one rule back there that I said you have to remind yourself of. And what is it?
Just have the accept state go back to the start state?
Yeah, you have the accept state go back to the start state, but there's a subtlety which comes up occasionally while you want this. You actually put a new start state with an epsilon transition there. And then the accept states go back to that one. Okay, and there are some situations, particularly if this is also an accept state, which explain why you need that. But it certainly never hurts to have the extra start state with an epsilon. Okay, why you actually need it, I'll let you convince yourself with some examples. So now we have an NFA for the whole thing. And so I've given you abstractly over there in a formal sense how you go from a regular expression to an NFA. And now I've given you a particular example and done it that way too. Yeah?
I don't think that NFA is quite right, because
Oh.
it doesn't accept the empty string, which you would get if you had 0 of AB minimum and you use extra accept state that's like an epsilon branch in the very start state. So
Okay, you're saying this thing contains the empty string. I mean, sorry, this contains, the empty string because it has 0 or more repetitions of this. Okay. And you're saying this doesn't accept the empty string. Yeah, what was your comment?
Make the start state and accept state. Well, the new start state.
Well, you could make the start state an accept state, that's true, but we have to follow the rules. Okay? So the question is, why didn't the rules give us... let's first of all be completely sure that this doesn't seem to work. So epsilon, epsilon followed by A, no, we're in trouble there. Epsilon, epsilon followed by A, we're in trouble there. Why? Now, did I build this according to the rules? No. Why not? What happened?
The 2 arrows should loop back to the start state, the old start state, but you still have the new start state. That one should be the accept.
Okay, so you're saying when you look in the book at how you do star,
Yeah.
that's what it tells you to do?
Yes.
Okay, so when I said over here, remind yourself how to do star, I should have actually done it, so I would have remembered myself how to. So let's do this abstractly. When you want to do star of R1, so here you have the start state for R1, and you have your finish states, okay? And so this is the NFA for R1. And when you want to do a star, you're telling me to do what again?
You take the accept states and you do epsilon transitions back to that start state.
Right.
And then you make a new start state that epsilon transitions to the old start state, and that new start state is an accept.
The new start state is an accept?
Yeah.
Yes. Yeah. Okay. Yeah, right. So when I told you to look this up yourself, probably because I, at that moment, couldn't remember how it was done, and I should have just stopped and figured it out. So this is how you implement a star in general when you have an NFA. And why? Because this is the regular expression here to the star, which includes the possibility of the empty string. Okay? R1 might not have had the empty string in it, but once you put the star on it, that's 0 or more times of R1, which means the empty string now should be in there. And so by putting this in here with this is the new start state with which is also an accept, and this is an epsilon transition to the old start state, this accepts now the empty string. And then this is the right construction. Okay, so now with this general rule, we have to always follow the rules. Let's fix what happened over here. When we were doing the star, I didn't implement the star correctly. Implementing the star correctly would have made the new start state an accept state, and these guys go back to here with epsilon transitions. Okay? Okay, so now we've built the NFA according to the rules. We're completely legal. And it looks like at least the problem that was pointed out here has been corrected. The problem that was pointed out here is that the NFA that I had a minute ago didn't accept the empty string, but now it does. Okay, because that's an accept. It's both a start and an accept. And thank you both for helping me through that one. Okay, so I've shown you in general how to go from a regular expression to an NFA that recognizes the same language that's described by that regular expression, and then we did a particular example to make that concrete. Now, the theorem that used to be on this board was that a language is regular if and only if it's described by a regular expression. So we've done half of that. We've gone from there exists a regular expression for this language to there exists an NFA for that language. Now we have to go backwards. We have to go from there exists an NFA or a DFA for that language to there exists a regular expression for that language, which describes exactly the same thing. Now, this is the harder of the two directions, or maybe not. Maybe I shouldn't say it's the harder, but anyway, it's got more moving parts. And I only have about 4 minutes left, so let me just at least introduce some ideas, and then on Thursday we'll finish this. Now, I don't remember. There may be. Yeah, I think there are some homework problems that are due for Thursday that require going from the NFA to the regular expression, and I'll take a look at those once class is over and decide whether or not you've seen enough material to be able to do that. And if I decide that you haven't seen enough material, then I'll put a note on the class website that you can skip or defer those particular questions. But anyway, let me get a little bit of a ways into here. What we're going to do, okay, so again, the lemma we want to prove is if the language is regular, then there is an NFA, there is a regular expression for A. That is a regular expression that describes A. And in fact, the way the proof is going to go, we're going to start out with a DFA M, call it M, for A. And we know that there is if the language is regular, then of course there's a DFA. And the first thing we're going to do is we're going to construct what's called a generalized NFA for A. So we're going to be building a certain kind of it's an NFA, but it violates some of the rules. It's slightly different. And then what we're going to do from that is we're going to successively modify the NFA one state at a time. To create the regular expression. So in fact, this modification is elimination. We're going to eliminate one state at a time from this GFA until finally all we have are a start and accept state, and then along that edge is is the regular expression for this particular language. Okay, well, that's just an advertisement for what's coming up, and we'll do that on Thursday.